welcome back to another fresh video, 11.2 series. We're going to talk about harmonic and telescoping series here. So we're going to introduce them, talk about them, see what makes them tick. The two specific series that we're going to look at, it almost makes no sense why we give them a name in the first place, because there's just one harmonic series that we're going to talk about. Telescoping series, on the other hand, there's actually quite a few of them. And talking about them in any detail is just interesting because of the way that this partial sum sequence turns out to look like. And it makes them surprisingly easy to work with. So let's begin with talking about the harmonic series. And so our fundamental question here is, why does the series from n equals 1 to infinity of 1 over n diverge? So I'm just going to straight off the bat tell you it diverges, right? But why? How is this clear, right? And as we can talk about in a later video, which will make more sense once we talk about the integral test, but we're not there yet. This turns out to be one of those special cases where if you modify it just slightly, it ends up converging. But this specific series does diverge. So let's just briefly examine the sequence of partial sums, right? So we know S sub 1 is 1. S sub 2 is 1 plus 1/2. S sub 3, which, we can write it as 3 halves, sorry. S sub 3 is 3 halves plus 1/3, which is, and you can, do the fraction algebra. I'm taking a few shortcuts through this just for the sake of making sure we're clear on what. Sorry, that's 11 over 6. I'm sorry. Maybe I shouldn't skip any steps. Clearly, I can't think and do the math at the same time. So 11 over 6 plus 1/4. All of these, right, if we're trying to combine them, you're just going to try to get a common denominator. And 6 and 4, the least common denominator is 12. So we end up with 22 plus 3 over 12, which is 25 over 12. Okay. S5 is 25 over 12 plus 1/5. Now, in this case, the least common denominator is 60. So 5 times 25 is 125 plus 6 over 60, which is 131 over 60. We're not terribly clear yet what is happening here. Of course, this is a monotonically increasing sequence. Is it unbounded? So there's a couple of different ways of thinking about this particular example, but maybe the monotonic sequence theorem isn't going to get the most direct way. So here's an interesting perspective on this series. Let's consider the function 1 over x over the interval 1 to infinity. Okay, and I'm going to draw here a picture which is going to superimpose both the series and the improper integral of this function, which is to say, so I'm going to draw here first basically a representation of the series. Okay, the width of each of these bars is going to be equal to 1, and the height is going to be equal to 1 over n. So we have 1, 1, 1/2, 1. So the width is 1, the height is 1/2. Then 1/3, then 1/4, then 1/5, then 1/6, then 1/7, and so on, right? Okay, so adding up the heights of all these bars infinitely, right? So this goes on forever, is the sum of this sequence, of this series, which it may not add up to something. It may actually be infinite. And importantly, this is also representing an overestimate of the integral of 1/x. Why an overestimate? Because the sequence a sub n equals 1/n is also the ceiling function for f of x equals 1/x, right? So if we think about, we're talking about discrete steps here, right? So at 1, we get the term 1, and then that doesn't change until we hit 2. So it's flat across. It's constant until we hit 2. In other words, we can see that because it's the ceiling function on this function on f of x equals 1/x, then the series 1/n has to be greater than the integral from 1 to infinity of 1/x dx. However, here's the rub, right? This is basically, we're modifying the integral comparison test that we developed in section 7.8, right? Since the improper integral 1 to infinity 1/x dx diverges, in other words, is infinite, so too must the harmonic series, which is the series of 1/n. Crazy, right? This hints at a new technique coming soon. We're not ready to talk about it in a further detail, but we're going to generalize that strategy as well to talk about something called the integral test. Now, here's the rub. So this works because we've found a function that it is the ceiling function for. It also doesn't tell us how quickly it diverges. So the harmonic series is very interesting in the sense that it actually grows very slowly. It grows approximately logarithmically, which means even though it diverges, so eventually it will reach larger and larger and larger values, it takes a really long time to get there. And it's there's some inequalities that we can use that are hinted at in the textbook that allows to estimate how many terms it would take for the partial sum to reach a certain magnitude. So it takes even a long time for it to get to pass 10, to pass 100. I mean, that is just beyond the scope of our quantitative reasoning. So maybe it's best if then we move on to telescoping series. Telescoping series are really fun and interesting because of the way that the terms in the partial sum decompose. So we're going to consider the series, and there's a handful of these, but this one is pretty standard. So we're going to modify this by 1/n times n plus 1, okay? Now, writing it this way isn't all that helpful. It may be helpful to write it as the sum of 1 over n minus 1 over n plus 1. How do we change the form of the terms of this series? It's an application of partial fraction decomposition. So we don't need to hash out the details of that. Of course, if you really wanted to see it, then you could always ask me. But it's the same technique that we would use in section 7.4, which is we have two linear terms, set up the equation, solve the corresponding linear system, and then you would get a equals 1 and b equals -1, and that's it. So here's the idea. Because this is an equivalent form of this series, let's try to figure out what the what the sequence of partial sums looks like, right? So S sub n is the sum from k equals 1 to n, right? So remember, k is that dummy variable. That just says, okay, we're adding up all the terms up to and including n. So really what that looks like is we're going to have the first term, which is 1 over 1 minus 1/2 plus 1/2 minus 1/3, right? Plus 1/3 minus 1/4 plus ... so on, plus 1 over n minus 1 over n plus 1. This is a finite sum, and here's the cool, interesting part of this, right? Let me use a different color. These cancel. These cancel. There's another 1/4 in here that you would see if you wrote it all out long ways. That would cancel. And there's another 1 over n that would cancel here as well, with the 1 over n that we see. You can't see it because we didn't write it out fully, but you could see it. For instance, if I wrote out another term, the penultimate term, which is 1 over n minus 1 minus 1 over n, right? Now you can see it, right? Okay, so the whole point of that is that all of the middle terms collapse. I guess a term for it is telescope, right? You collapse in on themselves, and we just get the expression 1 minus 1 over n plus 1. So the series, right, converges, and I claim it converges because this sequence will converge, right, to limit of 1 minus 1 over n plus 1. Though 1 over n plus 1 gets smaller and smaller, so that is actually going to become 1. Crazy, right? But we can adapt this to new and interesting series too. So we're going to see one more example. We're going to determine whether the series n equals 1 to infinity of ln of n over n plus 1 converges. Okay, so what's the idea? So we're going to notice that by properties of logarithms, ln of n over n plus 1 is equal to ln of n minus ln of n plus 1. Well, that's going to give us a telescoping form for the series. So S sub n is going to be ln of 1 minus ln of 2 plus ln of 2 minus ln of 3 plus ... plus ln of n minus ln of n plus 1. And so we get the same pattern, right? So these cancel. There's another ln of 3 that would cancel with that one. And the ln of n's would cancel as well, if we could see the other ln of n. And so all of the middle terms collapse, and we just get ln of 1 minus ln of n plus 1. ln of 1 is 0, so we get negative ln of n plus 1. Okay, so this is the form for the sequence of partial sums. So this series converges if and only if the sequence of partial sums converges as well. In other words, if this sequence diverges, then so too must the series. And we find ln of n, or n plus 1, it doesn't matter, does diverge, right? So the series diverges. Even though we had that nice telescoping pattern, sometimes it doesn't work out, right? In the next video, we're going to start talking about some more concrete ideas of how we can determine the convergence of a series, including a first test that we can use. And that is going to set the tone for basically what we're going to do for the rest of the chapter up until the power series sections, which is, given a series, we will have a set of tools to determine whether it converges or diverges.